Here we go. Good morning, everyone. Hope you're all doing great. Assignment 1, by my best knowledge and observation, seems to be finished marking. So, I don't want to make any guarantees because things always seem to go wrong at the last moment. But assuming that there are no catastrophic grading shenanigans, you should get your feedback by the end of today. And also term test grading is underway and you'll get that back by the VW date. So, we're going to keep talking about strings. And hopefully today will be the end of the silly contrived linked list example. We're putting a weirdly large amount of effort into showing how an interface can have multiple implementations, but I figure it's not a complete waste of our time because we're also generating a nice and helpful linked list in C example. So learning outcomes for today are basically the same as the last few classes, except when we finish the string example, we're going to get into testing. So this is all pretty familiar. And then to be introduced in this lecture is create general case and edge case test data for an ADT and implement a test harness that automates the testing of an ADT. So, as of yesterday, we had started building a list. So we had a node type that was private to our string implementation that we used for linked lists. And we just barely started to use that linked list to implement the string interface. Question?
I'm just curious, when will we be done all the information for the assignment?
Ooh, excellent question. Hopefully today, because this is going to be the big discussion about testing, and this should have everything you need for the assignment. And yeah, the timing is rough, isn't it? If we were doing like a Tuesday, Thursday class in a regular term, you would have a week to do the assignment after I give you all the information about it. But it's not Thursday, it's Tuesday, and you have 3 days. Sorry. Ooh, where's my terminal? So as usual, let's SSH into whatever your UONet ID is at aviary.cs.umanitoba.ca. Move over to whatever directory you're using for Comp 2160. And let's get right into it. Oh yeah, I left my connection open before I went home and that made it complain about a broken pipe. You've probably seen that before, but in case you haven't, this swap file error is probably nothing to worry about. I'm just going to read it carefully before I go because it would be a real bummer to lose my file. Okay. The second item on that list, like 2 in brackets, looks like the solution we need to use, so I'll press R to recover. And we're back. Capital G to go to the end of the file. And we're good. Looks like we're going to destroy a string. But first we're going to do an invariant check for self. Since destroy string doesn't take any other input. There are no other assumptions about the input we're making other than this being good. This as in self, or the string pointer that we're passing. This is another little lesson in memory management. You might be tempted to just free self, but it has a bunch of other pointers that it managed. So we need to pretty meticulously free them all. Question?
What are the implications of not freeing them all?
You would just waste memory, and if that happens enough, then a variety of things could happen, like your system slowing down or eventually completely crashing. So yeah, we have to loop through the entire linked list and free every node. That's all there is to it. Additionally, note that when you call destroy string in another function, such as main, that pointer will still point to the old memory, the memory you just freed, that is. And it's technically possible to keep using or keep accessing that memory, but it's very dangerous because that memory is marked as free and could thus be overwritten at any time. It's a very similar story to stack corruption, which we talked about earlier. So I can't show you this right now because this isn't a main function, but I highly recommend setting any pointers whose memory you just freed to null. That way you won't attempt to access previously used memory, and dealing with null pointers is slightly easier than dealing with memory that you freed and can be overwritten at any time. So I'm just going to check our string interface to give us a sort of to-do list for the rest of this example. So make string, check. Destroy string, check. Need to write char at and our two getters. Oh my gosh. Oh, I probably have to delete that swap file. Aha. This is also something that you may need to do in your own command line adventures. ls-a shows hidden files, and now I see stringlist.c.swap, and I got to delete that. Oh, man. Guess I overwrote that algorithm for deleting the linked list. I'll just rewrite it quick. Okay, now we're back where we left off. I guess that swap file had the state that the file was in before today's lecture, and since we didn't delete the swap file before accessing the file again, it reverted back to that state. Strange. So let's do char@. This will be a bit more complicated than the previous char@, because now instead of array indexing, we have to do linear search. Probably seen this before. So for preconditions, as always, the invariant should hold. But we're also getting some meaningful input through the index, and we're making some assumptions about that, namely that it's a valid index into the string's characters. So we're going to check that with an assertion as well. So we're going to loop or iterate through the linked list and keep track of what index we're at. And once we find the char that we're looking for, we'll exit the loop, and count will have the index we want.
Should node on 142 be uppercase?
Sure should. Thank you. Regarding some of the preconditions and potentially violated assumptions, it's also good practice to actually check your preconditions again in your code and have a special case for handling it. So, for instance, say you're using char@ in a program that gets user input, and your user is a total dumb idiot who inputs an invalid index. Design by contract won't help you with that because it is only for preemptively debugging during the development process. For actually using the file, for actually using this code, we should check again. So if the initial input assumptions don't hold, then this if statement will be skipped, and we'll just return null, the end of string character, as a sort of error value. So I think I just explained this loop in terms of finding the index of a character. That was a mistake. It finds the character at an index. So the loop terminates once it gets to the correct index. And another post condition that isn't part of a function. The count should be the actual index. That is, this loop should work. This is a good illustration of how design by contract is primarily for programming errors. This assert won't get violated if your user gives you bad input or whatever. This assertion will be violated if you messed up the indexing on that while loop. Like if you did count is less than or equal to index for that while loop condition, count probably won't have the wrong probably won't have the right value at the end. Is that me? Nope. So what was I saying? Oh yeah, this assertion will only give you an error message if you messed up while programming, which is what design by contract is meant for. I guess this example isn't completely useless, huh? I'm able to give a lot of examples of design by contract. Don't you love self-documenting code? The char at index is the current character. Cool. Yeah, question? Yeah, that's just to sort of cover us for when we're using a release build and the preconditions, or all the assertions aren't checked. Yeah, like I said, if a user is entering input and they enter bad input, that's not design by contract's job to handle that. So we need to do our own sort of redundant input handling. This will come up in the third assignment, and I was pretty frustrated when I learned that it was a thing. Like, yeah, I already have asserts, don't make me do things twice. But it is good to have a plan for what your code should return given bad input. I'm going to have a pretty chunky assert statement. So the assertion so far is that the input assumptions hold. So the index is actually representing the index of a character in the string. And the thing we're returning is not the end of string character. Put a slightly nicer way, if the input assumptions were not violated, then we're not returning the end of string character. So we continue, or so either input's good and we're not returning null, or the input was bad and we are returning null. Basically checking that we didn't screw up any assignments to char at index and we had the return value set up correctly. Oh no, do I have a bracket matching error? Yeah, but a simple one. Cool. Now all we have before we can move on to testing is the getters. So get length is going to be very straightforward. I can probably copy and paste it from the previous file. But get contents is going to be awkward because if we just do the exact same thing as the array strings get contents, then we would, I don't know, return a linked list, I guess. That is way too much implementation detail for the user to know about. Ideally, all implementations of an interface would work the exact same. In fact, you probably can't even return the linked list without modifying the interface. Anyway, so to get around that, we are going to have to modify the interface a little bit. So we return a char array, and I suppose we could also make our linked list strings get contents create a char array and then return it. But then that gives us another set of implementation differences where the return value of get contents for the array version is managed alongside the rest of the string instance's memory and will be destroyed with the destructor. And then the linked list version would have a newly allocated string that the user is expected to deallocate space for themselves. That's a lot of responsibility, and worse, it's inconsistent. There are more solutions we can consider that get more and more awkward. Maybe we could allocate space for those char arrays anyway, and then keep track of the things we're returning from get contents and then deallocate them all when you deallocate the string. That's kind of nasty, kind of end up re-implementing a lot of what malloc's supposed to do. So to sort of solve that problem, we're going to use an output parameter technique that we used earlier in the course and include as a parameter the char array where the characters should be stored. That way, we're making it very clear that the memory used to get the contents of the string is to be managed by whoever's using the string. Actually, I'm going to call contents output instead. Okay, that's it. Not going to make any more changes. I'm going to take my sweet time deleting the old stuff to give anyone typing along more time to write that output comment. But if you miss it, don't worry. This will all be on the course website. I'm going to do the evil copy paste. Oh, phew. Oh, there we go. My connection to Aviary froze for a moment. So as always, the invariant should hold as a precondition. And then we also want the output array to have enough space to store the output, but arrays in C don't know their own length, as you know. So we're kind of pooched. We kind of have to rely on the caller of getContents to provide a char array that has enough space. Though we could also have them pass an integer length parameter for the length of the output array, and then take care not to write past that. I'm going to do that because we've already modified getContents a little bit. May as well do it more. And then, of course, we're assuming that output length accurately represents the size of output, but we're kind of back to the previous problem. C arrays don't know how large they are, so we can't check this, and we're just trusting the user to use it right and doing our best to make it resilient to failures. So we're looping through the linked list as usual, but we're going to stop if the index exceeds the output length. So output at index equals current character, and then we move current over. Pretty easy. And then we add the null byte Gonna have to think about this for a moment to get the indexing right. I think I'll do different cases for the different termination conditions of the loop. So if current equals null, then we haven't exceeded the output length. No, that isn't necessarily true because this is an AND. So if this is true, then we know that the loop terminated because the second condition was false. So we should add the null byte at index -1 in order to fit it in the array. So basically, if the output length isn't enough to store the entire string, we'll store as much as we can and then truncate it by putting the end of string character at the end of the output array. So if this hasn't happened, then index is not equal to output length. Since index started at 0 and is counting up, which I should probably actually do. Since it started at 0 and is counting up, we know that if it's not equal to output length, then it's less than the output length. So we can just throw the end of string character at the current index. Yeah, I think that's it. So post conditions. Well, of course, the invariant holds. And then I suppose we should probably check the validity of the output. Honestly, I don't feel like writing a loop to loop through the entire linked list and compare the strings character by character, because I really want to get to testing, and that's way more important at the moment. So I'll just write a to-do comment, and then it'll never be addressed, just like real to-dos. I told you I'm teaching you all real-world programming. Easy. This is a completely valid tactic in the real world. You will do this. Except, now hopefully you'll make an issue on GitHub, but in spirit, you will do this. So last up was get length. Then we should rewrite main a bit in order to actually have or work with the newly updated interface correctly. I should make a separate variable for contents length. Beautiful. This should, in theory, work. It probably doesn't. If the compiler errors are numerous, then I'm just going to skip to testing. I'm kind of wasting your time here. I will revise this so that it can work before I upload this to the course website. By now, you've long since learned the lesson that one interface can have multiple implementations, and seen some nice examples of linked list usage in C and design by contract along the way. I'm still going to at least try to compile it, though. Please have several errors so we could just move on. Yikes! Undeclared identifier null? I probably have to include stdlib or something. Oh, assert, implicit function declaration, definitely got to include assert.h. Expected identifier bracket, probably missed a semicolon. Didn't include string.h. Yeesh, this is a mess. Compile your stuff early and often, please. I will fix this later. Unlike that to-do, I will actually get to that later. Watching me fix compiler errors won't teach you anything that you don't already know. And you all gotta learn about testing. So basically, once you get above a certain threshold of complexity of your code, which you absolutely will if you write anything of value in the real world, well, that's when all the lessons of this course start to apply, but one particularly important one is that you gotta write tests for your code. Tests simulate human interaction with your code, and you use them to make sure that those interactions work as intended. Ultimately, you write code to run your code. And for now, a big part of this will be figuring out what data to use, so how to, or what interactions you actually want to simulate to get or to become reasonably confident that your code actually works. So there are three general classifications of input data. There's general cases, valid expected inputs. So on your stack, on the stacks in your assignment, you'll likely do general case input for just normal small integer values, probably small and positive. Yeah, it's basically stuff that you would often see being used with your code. There are edge cases. Edge cases are things that come up less frequently but are still valid. Whenever I'm testing something that takes integers, I like to use the edge cases use as edge cases the largest possible integer and the smallest possible integer. I believe there's a header file called limits.h that contains a bunch of constants like int max and int min. The largest and smallest possible integers are totally valid things to add to your stack, but if your algorithm relies on the assumption that overflow or underflow won't happen, then those edge cases will mess you up. So that's an example of how edge cases are things that your algorithm is made to handle, but isn't common, and you might miss how to handle it. Then memory leaks are memory leaks. You malloc something and you forgot to free it, and there are tools that you could use to help you verify that every malloc has an associated free. So we're going to use a sort function as an example. This is kind of interface versus implementation at it again. We do not care about the implementation of sort. It could be bubble sort, it could be quick sort, it could be BOGO sort, whatever. We don't care. What we do care about is the fact that it takes an array of ints to sort and the length of the array. So some examples of general cases are lists of length n for any positive number n. Contents of the list shouldn't matter for it, as long as it's non-null. And you could basically test any randomly sized list with randomly assigned data. Does this address yikes things with random numbers? Not really. Word of caution, you'll go into this in more depth in software engineering, the course. This course is kind of pre-software engineering. Your tests shouldn't include any random number generation because you want your tests to be deterministic. You want them to have the same behavior and return the same results every time. When it says randomly here, basically means random as in unpredictable. Hard code a list in your test program. You could even decide on what the contents of the list should be using a random number generator. Just make sure that it's the same thing every time, because there's nothing more frustrating than a test case that only sometimes works. So yeah, the expected output that you might verify with a test is that the output sequence is the same size. You didn't just grow or shrink the list while you were sorting it. And the output sequence is in order, so the sort actually worked. And that the output sequence has the same elements. There are some sorts that don't work by swapping, but by actually modifying the elements of it, and those are very dicey, and you gotta, in those cases especially, you got to make sure that once it's done doing its thing, the output sequence has the same elements as the input sequence. So we're going to do another Menti activity. We'll come up with some general case testing data for testing a substring function. So let me know if you need any clarification or even want to see the slide again. But try to think of some general test cases, so pretty common input, for the given substring function. Yeah, I should have clarified. A test case in this context is just the input to the function. So all three of the responses have gotten it right, although I probably wouldn't include the function name in the test case. So yeah, the first one is a normal string, normal inputs, and it'll probably, you would check that it returns probably something like test. Same with hello, we'll probably say he. Same with hello world. That K. That test case, that's a really good one. I would actually categorize it as an edge case, probably, because when you think of a string, you probably think of more than a single character, and when you're writing a substring function, you might not be prepared for the case in which start and end are equal to each other, in which case you would return a substring of length 1. And that's a good example of something that's valid, but uncommon, and you might not be prepared for. So keep Menti open on your computers, because we'll get back to this later with edge cases. But before that, I'm just going to talk about edge cases. So recall that edge cases are things that are valid but look weird. Some examples of this for a sort are a list of length 0. That's valid. I could give you an empty list and say, sort this. Your algorithm in this case should probably just return the list without making any changes, but you could totally imagine an algorithm that directly accesses the element of the list at index 0 and assuming that it's there, which would misbehave on a list of length 0. Same with a list of length 1, valid but weird. A list that's already sorted, you want to make sure that your algorithm doesn't just mess it up. And reverse sorted numbers, that's sort of deviating from the typical case of a list of numbers you chose arbitrarily. Then identical numbers. And yeah, that's all. Test cases for sorting that are valid but unexpected, uncommon. You know how it is. So let's think of some weird test cases for a substring function. I'm actually going to change to the Mentimeter, advance it, and then go back to the slide and talk while you guys can enter your answers. I keep thinking it's on another desktop. So yeah, your answers should include the inputs to the function. So the slide just says, what does the string contain? But or as we saw in that substring of length 1, because the indices were identical example, you should also include the start and end indices. And also, you don't really have to do this. I have no way of enforcing it. But I would also suggest writing down in your answers the expected outputs of those inputs if substring works correctly. So in your testing program, what would you compare the outputted string to make sure that substring actually worked? Excellent first result. An empty string is completely valid, but weird, and I could totally see anyone making an algorithm that assumes that the string has at least one character. Ooh. Very interesting second response. Not sure how you would represent an infinitely long string, but this sort of reminds me of stuff that I would do with theory of computation, computability theory. Take Comp 3030, it's awesome. And if your language has a way of representing infinitely long strings, then yeah, your substring method should cover that. The third response is another really interesting one. And it's not really an edge case, because an edge case is a test case that is valid but looks weird. So null is probably not a valid input to the substring function. Your preconditions and assumptions about the input you want to make are up to you, but it would be a very common precondition to say that the input string must not be null, which would disqualify that as a test case. And similar story for this one, actually. An empty string is a great test case, but negative indices, that'll never give you anything useful. It does look weird, but it's not a valid test case. So stuff like this should be caught by design by contract rather than tested against. Still really good ideas, though. And then it looks like two responses with similar ideas. That is, putting the null byte in the middle of the string. You're probably still salty about that one test case in assignment 1. And yeah, excellent. The test cases should, or rather, a string with a null byte before the end is technically valid, but deeply stupid. I say stupid in a way that complements your ability to make edge cases. Good job. So yeah, that's perfect. And then test 3.3. I was about to say that's a typical case. That's not an edge case. But as I said earlier, the indices being equal is a very good edge case because you might not consider the case of a substring of length 1 and how you should handle indices that are equal. So I'll give like a little bit longer for responses to trickle in, but I think that'll be it. If you suddenly think of any and want me to verify whether it is a test case, put your hand up, I guess. So this actually came up during the discussion of edge cases. So thanks to whoever submitted that. Why is null not a good value to test even as an edge case? Because, like I mentioned, the definition of an edge case is valid but looks weird. And most of the time, null is not a valid input. Of course, if you have code specialized to reject invalid input and you want to test that it actually does, then answers like null or negative indices are a good idea. Sort of depends on whether those invalid inputs would ever be used in substring. If it's only ever used internally, you could rely on design by contract to catch it before it happens. But if the things you pass to substring could be user input, then you'll want to make sure that you have code to reject invalid inputs and that it works properly.
Maybe it is a linked list or something.
Oh, maybe if what is a linked list?
Like because for linked list, we use null all the time.
Oh yeah, true. Yeah, if you're testing a linked list, then indeed null is a valid pointer for next, so that you would have good reason to pass it into a function that takes a linked list node. This slide should say, why is null not usually a good value to test? Nothing in sufficiently advanced university subjects is actually black or white. It's all usuallys and probablys. So, got some test cases. You did a pretty great job of making some up. And what do you do with the data? So there are two types of testing: manual testing and automated testing. I'm just going to try to turn down this volume a bit. Hear an annoying buzzing, and that should probably fix it. So, manual testing. Probably very familiar with it. So first you change the main function of your program to accept input on standard input, call the function you're testing, and write output to standard output. Run the program, enter whatever test case you're on. You actually have to type it in like some kind of animal. Check the output manually, and then rerun your program, or hopefully it takes input on a loop and you can just keep running it. And yeah, exhaust all your test cases. Did it all work? Cool. Or not. And then you do that every single time. You do everything manually. You type stuff and you use your eyes. That's not sustainable whatsoever. You might be able to get away with it on a first or second year assignment, but third year onwards, and like, who actually cares about preparing for later in university? In the real world, that won't fly because the programs that you're working on will just be way too complex for that. So why are we even here? We're studying computer science because we're lazy. We have some repetitive process that we want to automate that lines up with the entire motivation for programming. So instead of entering your test cases manually again and again, write a program for it. So automated testing. You write code to test your code, which we refer to as test scaffolding. And look at an example that you've already seen before and probably spent a lot of time already looking at. Do I really need to open this? I will. It's probably on Aviary. So yeah, what was given to you on the first assignment is a perfect example of a test harness. If you have your is-balanced functions, it would get real tedious real fast to write the empty string and then a pair of parentheses, then a single closing parenthesis, then a single opening, then multiple pairs, then inverted, and then also, I don't know, write ASCII art of the Infinity Gauntlet by hand every time. That's not going to fly. So this test harness, yeah?
So to clarify, is this insert automated?
Yeah.
So you still have to type everything out between the sound, right?
Well, I guess you have to type everything out once. And by that definition, it is manual unless you use ChatGPT or something. But once you've written it all down, you can have the program run the test cases automatically. I totally lost my train of thought, so let's just get back to the slides. So some guidance for actually writing a test harness that'll be useful for assignment 2 is here, because this only had one function, or this is Java code, so one method to test. So it was very straightforward that you should make one test for that, one test function for that one function you're testing. But a stack is a bit more complicated than that, with a whole interface that you're given. So it's worth talking about how to organize your tests when it gets a bit more complicated. So one guideline is that each test function should be as atomic as possible. Atomic in this case means just one thing. Actually, does it say that? Yeah. It should test one thing and one thing only. With that list example, testing that the list is actually sorted, like the numbers are in order, should be a separate function to one that tests that the length of the string is the same. Yeah, and test it well. The data for the test belongs in the test function, which can mean either passing it as a parameter when you're dealing with multiple different test cases, or even just hard coding it into the test function itself. I strongly recommend letting your test functions accept parameters like how test balance does. And that lets you generalize it and more easily test multiple cases. And then the main function should only call other functions, which means that your main function in your test program shouldn't have any of its own logic. It should leave all of the actual computation to the test functions, and main is just a way of running them. So I think you have everything you need for assignment 2 now. Enjoy the week that you get for it. So yeah, we've basically finished our discussion of ADTs and interface versus implementation. I'll polish up the different implementations and post a complete example on the class website. And yeah, as of now, you should be able to implement a test harness to automate testing and create general case and edge case data. Cool, I guess we're about 5 minutes early. Have a great day and good luck on the assignment.